Dennis, should I start here? Okay, welcome to the third class, third lecture. So let's start by summarizing what we saw yesterday. Yesterday we were talking about the quantum spin chain. We had the Hilbert space, which was the tensor product of the vector spaces for each of the spins. And we had the Hamiltonian. So this was a one-dimensional system. And what you learned was to build the Hamiltonian. And we also had the translation operator. These two operators commuted. So we could simultaneously diagonalize them. We would get the eigenvectors, which were characterized by two eigenvalues, one for each, the energy and the momentum. And then we exploited some relation between the energy and momentum and the scaling dimensions and the conformal spin, which is valid at criticality, to extract information to extract precisely universal information of the quantum phase transition that we had for the critical magnetic field when we choose h equal to 1. Okay, and this is a plot of something that you did yesterday in the tutorial. Very good. And this was an approximate relation. There were corrections that were going as 1 over n squared. And that's why you would not get exactly so that's why after rescaling energy and momentum, we would not get the exact solutions. So what we would need to do in order to get better numerical estimates would be to go to larger n, larger system sizes. But of course, there was an exponentially large computational cost. The computational cost was exponential in n, so we have a limitation there. Very good. Today, I want to talk about something. Oh, no. Yeah, and this is a reminder to myself to tell you that please make sure that you completed the exercise that you had yesterday in the tutorial, because next week we'll go back to that. Actually, the homework that you will have at the end of the week will be building on this, so make sure that you get this right. And also next week, we'll continue where we left it. So today we're going to deal with another class of system. Yesterday was one-dimensional, it was quantum. Today it's going to be two-dimensional, it's going to be classical. We're going to deal with, again, a spin system. So we'll have on a square lattice, we'll put classical degrees of freedom, spin up, down. Okay, so it's again an Ising model. And we'll have some interaction between nearest neighbors, which is going to be ferromagnetic. So each spin can be up or down, and we're going to be favoring, at least at low temperatures, the two spins. The neighboring spins are aligned. Very good. So what do we want to do with this? Well, we want to compute, instead of a Hamiltonian, the important object today is going to be a statistical partition function. Z, which is defined, what we are going to do is we're going to take every possible configuration of the spins. This will denote a configuration of all the spins. So a choice of up, down, up, down, up, down, plus 1, minus 1, etc. And we're going to attach a weight to that, which is going to be proportional to exponential of minus the Hamiltonian divided by t. Hamiltonian evaluated on that configuration. And so the partition function is just going to be a sum over all possible configurations of those weights. Okay? The usual Boltzmann weights. We're doing statistical mechanics. So that's going to look like this. We're going to sum over all those weights. And now this will also look, once we replace the Hamiltonian, will look like that. So it's going to be a sum over possible spin configurations, and then we'll have these weights here, minus sum. This is going to be a sum over nearest neighbors of, there are two minus signs, so 1 over t, sigma I, sigma j. Okay? So our goal is to compute this object, this partition function. So we want to compute this guy. Okay. And you know that from the partition function, we can extract all the properties, statistical properties of the system, say the free energy, or I'm not going to go into this, but there is, say, a free energy that would be defined as minus t times the log of the partition function, and taking derivative with respect to the temperature or other parameters, we would get all the physical observables. So I'm going to focus on computing this object. There is a reason that's of interest. Right? We can extract all the statistical information from the system once we understand how to compute this object. OK, so what I want to do then today, the goals for today, are going to be first, compute Z. And we could do this. There are different strategies. One could be Monte Carlo sampling. Where we manage to identify what the most important contributions to the sum are, and we shall restrict our attention to those. But we will not be doing this. And the strategy we'll follow will consist in building a transfer matrix. That will be some matrix M, such that the partition function can be written as the trace of some power L of this matrix. Okay? That's the first thing we'll do. Then the second thing we'll do is analogous to what we did with the quantum system. We're going to focus on a temperature, which is, we're going to set the temperature to being the critical one. There's a phase transition in this model, and this critical temperature is log of some concrete expression. So if we set the temperature to be this one, then our partition function, our classicalizing model, two-dimensional classicalizing model, actually, again, its properties are described by this, its long-distance properties are described by a CFT, which happens to be exactly the same CFT that we studied yesterday. Okay? This time, we're going to, so our second goal today is going to be to, again, extract numerical estimates for, this time, the scaling dimensions and the conformal spins, as yesterday, but also this time we'll add the central charge. Okay? It's another parameter which characterizes the universality class. And we'll extract this from M, from this transfer matrix M, and also from a translation operator that will be very similar, or actually the same as that we used yesterday. So there will be a translation operator. And then these two will commute. And so we'll proceed by diagonalizing simultaneously the transfer matrix for the partition function and the translation operator. And from there, we'll be able to extract all this information. And finally, the third goal for today will be to explore a claim. And the claim is that a 2D classical statistical system is closely related in some sense to a 1 plus 1D quantum system. And when we'll see that we're extracting the same conformal data here as yesterday, right? Yesterday we dealt with a critical one-dimensional quantum system. Today we're dealing with a critical two-dimensional classical system. We extract the same. We see that both systems are described by the same CFT. that's already indication that there is some relation between the two, but we'll have the tools to investigate numerically this relation a bit more. Very good. Okay, so let's get started. I want to do this in a place that later I can refer to, so maybe here. Screen goes down here. Okay. So transfer metrics. Transfer metrics is some metrics that when you exponentiate it and take the trace, sorry, when you compute some power and take the trace, you get the partition function. Now, if this matrix, if we diagonalize it, if we write it as its eigenvalues, if we write it in its eigenvalue decomposition, then what's clear, if we find this matrix, it's clear that this expression here, take m to the second power, this is just this times itself. There is a delta with the basis, so you can check that indeed this is going to be just eigenvalues squared. That's what happens if you take a diagonal matrix and you square it. You just get the diagonal elements get squared. So in general, if you put here elf power, we'll have elf power here. So now we just need to take the trace of this, but the trace will give you that this is, if these guys are normalized, what you will see is that this is going to be a sum of the eigenvalues of the transfer matrix to the elf power. Okay? So the way we will evaluate the partition function is by diagonalizing, by building the transfer matrix, diagonalizing it, getting the eigenvalues, and then taking the elf power and summing over those. Okay? Good. So now I need to do some drawing here. So I'm going to do something slightly weird. I'm going to put the spins. The square lattice is going to be tilde. And that's just one possible representation we can use, which I find very simple. So that's my choice. You could choose something else to build a transfer matrix. So these are the spins. And now the Boltzmann weights on these spins are connecting nearest neighbors. So there will be Boltzmann weights like this. Right? Each line denotes nearest neighbor pair. Okay, and then I have some form of periodic boundary conditions, which means that this one is nearest neighbor with this one, and so on. Okay? I have periodic boundary conditions on all directions. Okay, so what I've done is you can see the square lattice. It's been tilted. And now I'm identifying these indices, sorry, this part with this part. So this connection here is saying that this spin is nearest neighbor with this one. See? This connection goes back here. Okay, so, and now what I'm going to do is I'm going to label a subset of these spins. I'm going to call this sigma 1, sigma 2. This one is sigma 3. I'll have a sigma 1 tilde here, sigma 2 tilde here, sigma 3 tilde here. And what I'm doing is I'm reorganizing, or I'm trying to organize the partition function, the sum in the partition function in a convenient way. So I've so far decided to single out some of the spins. I use notation sigma for some of them, mu for the others. These are just variables that take two values, two possible values, plus or minus 1. Okay. And now what I want to do is I'm going to define, I'm going to break the system. I hope the colors make the difference clear. So this is some way of indicating that I'm breaking this structure into pieces. And now I'm going to define some matrix attached to the region here. Okay? So how do I do this? I'm going to define this matrix M is going to be a function of sigma 1, sigma 2, sigma 3, and also sigma 1 tilde, sigma 2 tilde, sigma 3 tilde. So far, it won't, for the time being, it won't look like a matrix. We'll turn that into a matrix later on. So at the moment, it's going to be an object with 6 indices. Okay? And it will be the following. We define it to be sum over mu1, mu2, and mu3. Okay? So sum over the spins inside the region of the Boltzmann weights of all the spins, the sigmas, the sigma tildes, and mu's. Okay, so I'm just going to start here saying, okay, have nearest neighbor here, sigma 1 and mu 1. So I'm going to put the corresponding Boltzmann weight, sigma 1 times mu 1. Okay. Now I realize there is also a connection between sigma 1 and mu 2. So sigma 1 and mu 2. Okay. Now it's time for sigma 2 with mu 2 and also sigma 2 with mu 3, right? Sigma 2 is talking to mu 2 and mu 3, and so on. And then eventually here, we also involve the sigma tildes. So in this, we also have sigma tilde 1, mu 1, sigma tilde 1, mu 2. And the last one is going to be sigma tilde 3 with mu 1. Okay, so what I'm doing is I'm attaching some tensor with 6 indices, 1, 2, 3, 4. So with the sigmas and sigma tilde as indices, and I'm performing the sum of the Boltzmann weights over the spins in between. Okay? Okay, so once I've done this, now I want you to spend a minute convincing yourself that the following is true, that the partition function is equal to m sigma 1, sigma 2, sigma 3, sigma 1 tilde, sigma 2 tilde, sigma 3 tilde. Okay. Now we'll put another copy of m with sigma 1 tilde, sigma 2 tilde, sigma 3 tilde, and double tildes. And this one, now I'm labeling the next row with sigma 1 double tilde. Okay. And then we have, so I'm saying there is another copy of M here, but it has these other indices. And finally, there's another one on top, which has indices sigma 1, sigma 2, sigma 3, and sigma 1 double tilde, sigma 2 double tilde, sigma 3 double tilde. Okay? And now we have a sum over sigma 1, sigma 2, sigma 3, sigma 1 tilde, sigma 2 tilde, sigma 3 tilde, and also the double tildes. Okay? Is it clear that this is the partition function? What we've done is we've made a partial sum over the mu's. Okay? So we wanted to compute the sum over all spins, and we made the partial sum first over the mu's. And then now we're summing over the remaining variables. Okay? And now I just want us for a second to start thinking about what a label I, or a new index, let's call it alpha, which is sigma 1, sigma 2, sigma 3. So what I mean by this is that if each of these takes 2 values, then this alpha takes 8 values, right? 2 to the 3 values. And therefore, we can write this in terms of sum over alpha, alpha tilde, and alpha double tilde of this, what we now can call properly a matrix. Okay. Now M has 2 indices only. It's a matrix. And this is nothing but the trace of M to the 3rd power. Okay? Is that construction clear? We are trying to make a sum over many small variables, and we did a partial sum over some of those, and then we put together several of the remaining variables, and we organized this. It's just an organization of the calculation we wanted to do. Very good. So in general, what we're going to have is, here is our square lattice, which is tilde. And I hope I get this right. Okay, so now we have, if these are our sigmas, and we assume that we have n of such sigmas, and in this direction we have L, okay? Then our matrix M, the transfer matrix M, is going to be, it's going to correspond, roughly speaking, to this part of the partition function. And we'll have L copies of it. So the partition function is going to be the trace of M to the Lth power, okay? L being how many times we have the transfer matrix. And on the other hand, this transfer matrix will be, will have M, will have sigma 1, sigma 2, all the way to sigma n. Variables. So if we call it alpha and beta here, or alpha and alpha tilde, alpha is going to take 2 to the n values. Can you see? Well, okay, that's not the best place in the Blackboard to be writing. But what I'm saying is that matrix M is going to be a 2 to the n times 2 to the n matrix. Okay? Pretty much like the Hamiltonian that we had yesterday. 2 to the n times 2 to the n. Okay? So we'll use all these decompositions to input this into the computer. But in practice, we'll find it convenient to actually break M in turn into smaller tensors. So what we will have today is that this matrix say for n equal to 5, we have this matrix. This is alpha tilde. We're actually going to view it as a sum over certain tensors, A, we'll build a 4-dimensional array, tensor A. And so this is M, and it's going to be a combination of tensors, multiplication of tensors A, where this is again sigma 1, this is sigma 1 tilde, and here this index that goes around will correspond to the mu's. Okay? So it's going to be sum over mu 1, mu 2, etc. So mu 3, mu 4, mu 5 of a structure like this. That's going to be convenient because it will allow us to build the matrix M. We'll be able to reuse the construction for when we have n spins, or sorry, n spins in this direction, or when we have n plus 1, right? The difference will be adding one tensor in this construction. So we'll be able to systematically construct this transfer matrix for different system sizes. Okay?
Question. What does it mean when your lines intersect without a tensor in the middle? Like your sigma 1 line there on the left.
This one? Okay, let me delete it.
Ah, okay. And then you're tracing over the entire.
And then there is a sum. So okay. Now it doesn't.
Thank you.
Right? So that's what it meant. Very good. Okay. So, and actually, if you count the number of spins that we have in the system, number of spins, you'll convince yourself that we have 2 times n times L. Okay, this is the total number of spins that we have there, right? Because for every sigma, so there are n times L sigmas, and there are as many mu's that we have already made the sum. So that's the 2 here. All right, so we're almost ready to go to see Julia. Before we do that, let me tell you about, I need more space, maybe there. Okay. So we've built the transfer matrix, and now we are ready to explore RB, which corresponds to fixing the temperature to a critical temperature. And then there will be, so we just discussed how to build this transfer matrix. Okay. Now we'll build also our friend, the translation operator, which was like this. Okay, exactly the same from yesterday. We are quickly able to argue that they commute because, well, if you want, just use this was translation invariant by construction, but if it's not clear, just remember that we'll build it as concatenation of identical copies of a single tensor. Okay, and let's not get confused about the meaning of this index going around. Okay, and then it's clear that this is invariant in the translation, so if I do something like that to this, that's the same. You can reshuffle everything and get that this is equal to same construction. But now the translation is on the other side. So how do I do this? Did I do this right? Yes. Okay. All I did here is take this tensor, this one, which is identical to the rest, and move it here. So I'm just rotating the construction. But yeah, I get exactly. So this is if this was sigma 1, this is still sigma 1. I just moved the representation. And so these two objects are the same. That's the same as saying that these two guys commute. All right, so what I'm going to use then is something that you are familiar with, of course. If they commute, then we can diagonalize them using simultaneously. Let's call alpha the eigenvectors, lambda alpha the eigenvalues for t and for m and for t. Okay, that's very similar to what you did yesterday with the Hamiltonian. And now we go back again to Cardy and others in the 80s, and they actually made the prediction that at criticality the partition function should be such that there is an expression for these eigenvalues. And the expression is that these eigenvalues for the transfer matrix have this form. Which we see here the central charge, okay, the scaling dimensions, and the conformal spin. So the relation between momentum and conformal spin is exactly the same that we saw yesterday. And then there is some other relation, but yeah. So we'll have to take a log of this number to extract the scaling dimensions, and maybe we'll have to do something with the central charge. But this reminds us a lot about what we saw yesterday. So specifically what we're going to do here is we're going to say, OK, the scaling dimension alpha minus 1 is equal to n over 2 pi log of lambda 1 over lambda alpha. That follows from the first expression. So that's how we're going to estimate. We're going to always use that the identity has scaling dimension 0 to get directly an expression for the scaling dimension, one of the scaling dimensions of the theory, right? In terms of the logarithm of this ratio of eigenvalues of the transfer matrix. This is one expression, follows from here, and the other one is the same as yesterday. The conformal spin will follow from the momentum by just rescaling. Now this very much looks like what we did yesterday, but actually yesterday we had to figure out, we had to know more information. We remember that we had to shift by some, I had to give you just the first scaling dimension above the identity, so the identity we had scaling dimension is 0. I had to give you also the next one. Okay? Today we will not need that. And that's because in this expression, there is already a normalization that is fixed by conformal invariance, so we need less information. And on top of that, we'll be able to extract C, and this will come from looking at lambda 1, the largest eigenvalue here, which is e to the an minus 2 pi over n C, plus central charge over 12. So what we'll do is we'll compute lambda 1 for different values of n, okay? And then you can see what we have is that from this expression, what we have is that n times log of lambda 1 is a n squared plus 2 pi n c over 12, okay? So if we compute this for different values of n, what we can do is we can plot here n squared. We can plot here, so x is going to be n squared, y is going to be this expression here, n over log lambda 1, and we'll get some points here. And then by linear regression, we'll get that an estimate y as a, do I call it a? Can I call it a? Ax plus b. And so we'll estimate b this B will give us an estimate precisely to, from B, we'll be able to take, oh, there is a mistake here. Okay, so this is going to be B. Okay, so we can estimate the central charge. Okay, we have all the information there. We're saying the first eigenvalue, the largest one, okay, depends on the central charge and on n. And we have the ability to deal with different system sizes. So we'll use that ability to estimate how much the central charge is. Okay? So now we start doing all this. Are there questions? We have a minute. Please start your laptops. I'll start mine. Can we have the, how do you call this? Can we have the screen, please? Thank you. Okay, so you should have a notebook that I emailed yesterday. We're going to use that one. And compared to yesterday, the first thing we'll have to do is to start dealing with tensors, so matrices, instead of matrices, arrays with more than 2 indices. And so let me tell you how this works. Or again, you should figure it out by yourself. Here's a sample. So if we want a tensor with 3 indices, we can made of 1, so we can produce it. Oh, let me try. Let's see, kernel, start and clear output. Okay, that didn't work. That's fine. All right, so you want to create a tensor with 3 indices. The first index taking 2 values. The second the second index takes 4 values, and the third index takes 2 values. Okay, so you can do it full of number ones. You can do it this way in Julia. Okay, so Shift Enter, and we get exactly what we wanted. It's and this is how it's plotted. So the third index taking value 1 gives you a matrix which is 2 times 4. When the second index, when the last index takes a second value 2, the rest gives you again a matrix which is 2 times 4, and so on, as you would expect. Okay, another way of initializing a vector, tensor would be using this rand. Is it working? Sorry. Is this almost everybody following this? So we can also create a random tensor, then a tensor of shape 2, 4, 2, meaning 3 indices, the first index taking 2 values, the second 4 values, and the third 2 values and with random coefficients by using this expression. With tensors, we can also take linear combinations, so we can multiply a tensor A that we just created times 3, and then tensor B, which we just created, times the imaginary unit, and add them together. And if we do that, we get what we expect. Okay. And if you have a tensor and you forgot how the indices are organized, you type size of V, and this will give you a list with the 3 values of the 3 indices. The first one takes 2 values, the second 4, the third 2. And now an important function that we will need today when we deal with tensors is reshape. Reshape will allow us to join 2 indices together, or 3 indices together. And that's what we were arguing here when we were building this transfer matrix. We have the sigma indices, sigma 1, sigma 2, sigma 3, and at some point we call it alpha. Okay, we put 3 indices together. We'll do this with reshape. Okay, so for instance, this example is telling you B, we just checked it's a tensor with 3 indices. The first takes 2 values, the second 4, and the third 2. this command here says reshape B, which is this tensor with 3 indices, and then this is telling Julia how to reorganize these indices. So it's saying we're going to use from now on just 2 indices. The first one will take 8 values, and the second one is going to take 2 values. So the first one will be the product of these 2 indices, 2 and 4, give you 8. And the third one, sorry, the last index of this. So we're reshaping B, which had 3 indices, into a matrix which has 2 indices. And the association is this, right? We are taking the 2 first indices of the tensor into a single index. That's what we're doing. And yeah, shift enter. And if you have patience, what happened here? Yeah. So we had, if you check B, B was a tensor with 3 indices, and you will see that it has exactly the same components as C. Now it's a matrix, but the components one by one are the same, just organized in a different way. What you could do now is you can take C and reshape it. C is a matrix, right, of size 8 and 2. We can reshape it back to 2, 4, 2, so back to having 3 indices, and then check that indeed the difference between D and B is 0, right? We started with B, we reshape it back. Of course, we expect to get the same. And then if you want sometimes to see whether 2 objects are the same, you have this command is equal that says, yes, B and D are equal. And this is all up to numerical precision. So actually, I'm going to modify the second tensor by adding a small perturbation, 10 to the minus 18, and see, and it's still equal. Okay, they are still equal. If I change the perturbation to up to numerical precision, 10 to the minus 15, then suddenly these 2 objects are no longer the same. So this is equal will allow you to compare 2 tensors up to numerical precision. Okay. Very good. So now we have maybe everything we need about tensors to get started. So let's go to this partition function. Here we just define the critical temperature. There is a coupling that I never used. I don't even know why this is still here. So out. Very good. So we define the critical temperature, and from now on we'll just use this critical temperature. So let's see. I told you that we were going to break M into pieces. So let's look at this tensor A, and let's build it. This tensor A is going to be nothing but this is just a tensor with 4 indices that will take the following values. It's going to be the Boltzmann weight of all the spins appearing here. So e to the 1 over, now we're at critical temperature of mu1 or sigma 1 mu1, sigma 1 mu2, and also sigma 1 tilde mu1 and sigma tilde 2 mu 2. What am I doing here?
Sigma tilde.
There is no 1, no 2. Okay. Okay? So basically, we've broken the partition function into pieces, and this piece corresponds to just accounting for the Boltzmann weight between these 2 spins, these 2 spins, these 2 spins, and these 2 spins. Okay? This is going to be our unit. We're going to build M by putting together such units. So how do we go about creating this tensor in Julia? Well, I'll show you if you want, straightforward way. We're going to define a function Q of I and J such that it returns the Boltzmann weight. Sorry, the product of I and J with a minus 1. That why is this here? OK, I guess there is a typo. I should remove them. Oh, no, sorry. OK, that's good. So this function is going to do what? If you have if we input 1 and 1, it's going to multiply them. It's going to add them. That's pretty silly, no? We could return I times j. This is the same as I times j. OK.
But I and j, aren't they 1 and 2, not 0 and 1? Or minus 1?
Oh, that's right. That's the problem I was trying. OK, yeah, look, this comment is explaining. All right, so indeed, when we want to use indices, we cannot use any value we want. So instead of using minus 1 and 1, we'll be using 1 and 2. OK? And this is why we needed to do this. But basically, this is going to split plus 1 or minus 1, depending on whether I and j are the same or different. OK? So thanks for rescuing me. So what we're going to do then with this function in place is we're going to initialize this tensor, which has 4 indices. Each index takes 2 values. Okay, this is our tensor. Now the only problem we were facing here is that we've been talking all the time about sigma 1 being plus 1 or minus 1, but in practice, this index will have to take values 1 or 2. Okay, and this function is just translating between the 2 options. And what we're going to do then is we're going to write this tensor. We're going to fill it with the coefficients that we want. Okay, so you give me I, j, k, and l. Okay, for this choice of indices, the coefficient in the tensor is going to be precisely the Boltzmann weight that corresponds to that configuration I, j, k, and l. Okay? And we're going to do this for all values of I, all values of j, all values of k, and all values of l. So what this expression here, what these 4 consecutive for loops are doing, is they are initializing this tensor such that it has its 2 to the 4, so 16 components, equal to the corresponding Boltzmann weights. Very good. And this might not be the most elegant way of doing this. Julia has other options. There is this list comprehension syntax that allows you to do the same in a more compact way. And I just leave this here as a sample of code. Sorry, I should shift enter first the other one. Yeah, and so we check that this is another way, more compact way of writing the same. I've prepared on top of prepare A. Here I've prepared B in a single line, and A and B are the same. So I leave that to you. If you want to learn, for instance, this list comprehension, it's very useful, but I'm not going to use it today. I just left that as a sample code. All right. So now what we want to do is we want to compute M. And the simplest example that we could have would be when we put together 2 tensors. Okay, like this. M, this will be sigma 1, sigma 2, going to sigma 1 tilde, sigma 2 tilde. Okay? So what we need to do now is to learn how to multiply together 2 tensors. Okay? And this is what this box is doing, this cell. We're doing this in this cell. So I'm going to call this A. Okay? And it's going to have, you see, the result of multiplying these 2 is a new tensor that has 4 open indices because we took the trace with the others. So it's going to be an object like that. And so I'm going to organize this in the following way. We'll have A. Second copy of A. I'm going to call this index L, N, J, M. Good. And this is going to be I. And then this is going to be K. And this is also K. because there is a trace over it. And so if you look at, and the result is going to be AA, where this is L, this is N, this is J, and this is M. Okay? And this expression with these 6 for loops from here to here, okay, is just saying for any value of L, N, J, and M, okay, take these 2 tensors, multiply them, and and take the sum over I and K. So you can see that in this expression, the index here, the index I appears in here and in here, right? And the index K also appears on both tensors. And when we make a sum over those, that's when we're contracting these indices together. Okay, so that's how we would proceed. And now the last step to turn that, we want to turn that into M alpha and alpha tilde. What we have to do is we have to reshape this object with 4 indices into a matrix with 2 indices. Okay, and that's the last expression down here. I'm still calling it. Let's still call it AA. And now single index, but a bit thicker, implying that it's the composition of these 2. So there is an index here, say alpha, which is equal to Jm. And there is another index here, let's call it beta, which is equal to L times N. Okay? L and N composed together. So again, what we've done is, first we've created this single tensor, and then now we're seeing how to multiply 2 tensors together. The result is a tensor with 4 indices that we reshape into a matrix. Okay? And this is nothing but the transfer matrix for the case where we have N equal to 2. Okay? Just 2. 1, 2. Okay? But what we would like to be able to do is we would like to be able to build M, this transfer matrix, for the case where we have some generic N number of tensors A put together. That's what we would like to have. Okay? So we would like to build this when we have N such tensors. And we'll do this sequentially. What we're going to do, this is the next cell. Is we're going to write a function that will take some partial calculation here, which could account for several A's together already. I'm going to call this temporarily M, and we'll add an extra A to it. Okay? So the result is going to be MA. And then we'll put together these indices. And I think the result finally, OK, no, yeah. So this is still called MA. And now these 2 indices are together, so it's an even thicker index here and there. Okay. So we've used reshape here. Okay. And so if this was for N, if this was already accounting for N spins, and this is an extra one, now this is N plus 1. Okay. That's how we. And OK, that's, again, not the best choice of place in the Blackboard. So this is how this function that's called grow M, takes as an input a pair of tensors, this one, which is already accounting for several A's, and an extra A, multiplies them together, and produces a new tensor that indeed accounts for an extra A compared to before. OK, so the details are here in the function. I don't think it's, again, just very similar to what we have done before. Usually what you have to do is be careful with how you label things. Make sure you draw nicely the indices, the names of the indices, so that when you translate it into an expression, you don't get you get all the positions correctly. But there is no more than that to it. All right. So with that function that attaches an extra A to a pile of A's, what we're going to do now is we're going to build, having that function, we can build now our transfer matrix. The input will be tensor A and the number of copies of A that we want to put together. And what we're going to do then is we're just going to grow this one at a time, and we'll repeat this n times, right? So our goal is to produce this guy. And we're going to obtain this by first putting together two A's, then an extra one, right? We'll call this function that is called grow m to attach an extra one, and then an extra one, and so on. And the final result, when we're done with that, we'll have this final loop, which will actually make the trace. Okay? So this is a quick description of how we can use Julia to write this transfer matrix. Okay.
Good.
Yes?
Why did you use copy A, M2 copy A?
Right. So what I wanted to do here is I wanted to, I don't want to change what A is. Right. And with Julia, you have to know that if you give some variable to a function, and the function manipulates this variable, it changes the variable, not just inside the function, but also outside the function. So I was being careful. I just wanted to use a copy of A as opposed to A itself.
Okay. So that's like Python.
Yeah, yeah. So, Marcus, that's like Python, right? So you have to be careful not to, inside the function, you don't want to manipulate the input of the function unless that's what you wanted to do, of course. So that's why I use a copy here. Okay? Very good. All right, so we have this function that produces the transfer matrix, and now you can look at it carefully at home. What we need, we've built M for an arbitrary number of n of copies of A. And now we also build, or we have again, we discussed this yesterday, we can build a translation operator. That's exactly the same translation operator that we had yesterday. So I don't need to mention it or to explain it. And also, we're going to build a symmetry operator Z2, which actually is the same that we had for the product of sigma z's yesterday, but we're going to use product of sigma x's, okay, instead, just because that's the way the Z2 symmetry is implemented in this model. All right. So I have to accelerate a little bit because it's getting late. So what we have now is we're going to choose n equal to 10. We're going to consider the case where we put together 10 A's. We're building a transfer matrix with 10 A's. And then we're going to just build also the translation operator, the symmetry operator, and we're just going to diagonalize. This, if you replace M here with H, you should recognize this code. It's identical or very closely related to what you did yesterday. And so if we do that, grow M not defined. I forgot to shift enter somewhere here. OK, now it's working. So now we have produced this transfer matrix M. Okay, remember, it's a large matrix. It's 2 to the n times 2 to the n. So n should be 10 or something like that, not much larger. And now what we're going to do is we're going to exploit all the relations that we discussed before, which are right there, between the eigenvalues of these transfer metrics and the scaling dimensions of the theory. And this, again, I'm just taking the logarithms that I promised I would be taking and so on. So that's what this is doing. Okay. Once we have the eigenvectors of the transfer metrics, we can again evaluate how much the eigenvalues would be. And we do this here. And then, yep. All right, and we go, and this is, we're going to use pyplot to plot the results. But the point is that this is really very similar to what you did yesterday. And the results are going to be pretty much identical. Okay? So once you've processed all this information in a very similar way as we did yesterday, you get that your estimates for the scaling dimensions and conformal spins are the ones, or pretty much the same as the ones you got yesterday. Okay, so what's going on here? Well, yeah, okay. Let me mention, as I said before, we can also now use the fact that we can look at the largest eigenvalue, sorry, and estimate the central charge from this. And that requires taking a logarithm. And yeah, there is no surprise there. So it's computing that at the moment. It just did. Okay. So here you can see when you plot n times the log of this largest eigenvalue against n squared, you get a very nice fit. Okay, it looks like a straight line. This is for n equal to 2, n equal to 4, n equal to 6, 8, 10, 12 up there. And this looks like it's going to 0, but if you actually look at the coefficients of the linear regression, this is very simple. To make a linear regression, you can do it just by calling this function linear regression of x, of the values that you want to approximate. And then what we find is that there is an estimate of the central charge out of it, which is somewhere here. So one of the estimates is telling you that the central charge is 0.4976, and actually we know it's 0.5. Okay, so we have been able to extract the central charge. Okay, this is a bit rushed, but you have it all in the notebook. And then the last thing I want to mention, and we'll stop, is that what we've seen is that this transfer matrix M that we've built, okay, very much looks like the exponential of h from yesterday, minus h. So what this is the transfer matrix for a 2D classical system. And this thing here, oops. No, this one is, and this thing here is actually the Hamiltonian for a 1D quantum system. Okay? So in principle, these are very different systems that we have, a 1D quantum, a 2D classical. But in the end, they happen to lead to the same critical information. But actually, it's more than that. They seem to be connected in this way. Okay? When we took the log of the eigenvalues here, we got the eigenvalues of the Hamiltonian from yesterday. And so the last cell, what it's doing is actually going a step beyond. It's taking the largest eigenvector, the eigenvalue with largest eigenvector from this matrix, and it's asking, is it actually the ground state of the Hamiltonian that we had yesterday? It's asking this question, okay? And the answer is yes. It's exactly so the eigenvectors of this transfer matrix are the eigenvectors of the Hamiltonian. The comparison is only works if you actually choose you have to rotate the basis, so the Hamiltonian that you have to put here is sigma z plus sigma x. Okay, so I've changed the z's and the x's. That's because there is a convention in the quantum case to work with certain bases. And in the classical case, the basis is naturally the one that leads to this, okay? But the idea is that we've been solving, yesterday and today, we were solving essentially the same problem, okay? Even though we started from what looked like different problems, because we had yesterday a one-dimensional quantum system, and today a two-dimensional classical system. Questions?
You say the ground states are the same?
Well, this cell compares the ground state, looks at the ground state, looks at the first eigenvector of this, the eigenvector of the transfer matrix with the largest eigenvalue, okay? Looks at that, takes that eigenvector, and looks at how it relates to this Hamiltonian. And it finds out that it has the ground state energy of this Hamiltonian.
Okay, so
therefore, it's the ground state.
Between the eigenvalues and the eigenvectors.
No, now it's the eigenvector as well. Because there is only one vector that would have the lowest possible energy of the Hamiltonian. The Hamiltonian has a spectrum, has the lowest energy, and then all the rest above. If you have a state that has exactly the same energy as the lowest eigenvector, it has to be the eigenvector. Okay. In general, a random vector will be a linear combination of eigenvectors of this Hamiltonian, but then the energy of that vector that you have will be a sum of contributions from different energies. If you hit exactly the ground state energy, it has to be the ground state. Okay, so this was just to start you in this, and you can go now and explore whether this is also true for all the eigenvectors of n, right? And whether this is actually true. This is not just some, it looked like there was some relation, but now you could check whether this is accurate eigenvector by eigenvector as well. Okay, so tomorrow, so far what we've done is manipulate systems of spins, quantum or classical. We've seen that there is a cost, computational cost attached to that, which grows exponentially in the number of spins we want to consider. And that left us working with 10 spins, typically, in the quantum case. So tomorrow, but next week, we actually want to study the structure of entanglement in systems that are much larger than this, okay? And in order to be able to do that, what we'll have to do is to cheat a little bit. We'll be dealing with, so this is the Ising model. This is not a generic model. It's a very special model. It can be mapped into a free fermion model. And we'll be able to, tomorrow, to use that map to explore, to solve the same model again, but for n up to 1,000 spins, okay? With no problem. Okay, so that's what we will see tomorrow. All right, thanks.